Welcome back. This is part 2 of video lecture 7.1. I decided to break up video lecture 7.1 into two smaller videos so that you could take a break and a pause and it wouldn't be one single long video. But this is really video lecture 7.1 continued, part 2. And the reading for this part is back to chapter 7, now into section 2. Work and kinetic energy. Good. We're going to bring back kinetic energy that we talked about in the previous lecture, and we're going to introduce a new physics concept called work. In fact, I'm going to go straight into that definition here in just a second, but first, a word of warning. Work is one of those words that people use on a daily basis, and the everyday meaning and the physics meaning are not the same, as I know you can appreciate, and that we have to be clear and careful about using the physics definition when we talk about work. So now let me introduce the physics definition of work. I'm going to start with a restricted version. Okay? I'm going to take the following scenario. The first thing I want to emphasize is that work is done by forces, or a force, right? Work is done by a force. Let's write that down. Work, there we go, is done by a force. Done by a force. It's forces that do work. Not people. That's an everyday way of thinking. Forces do work. Okay? So when we talk about work, we're always going to say, what's the work done by this force? What's the work done by that force? That's how the physicist is always going to talk about work. So now my restricted version of work is for the case where the force that's doing the work is constant, right? Constant means not changing with time. I've got a particle, it's moving around. There may be multiple forces that are pushing and pulling. We're going to focus on one force at a time when we talk about work. And I'm talking now specifically about a force that's pushing or pulling with a constant push or pull. The force is constant. The force is not changing, neither in magnitude nor in direction. Okay? That's my restriction. In that case, I'm going to now start talking about how you define work done by a constant force. Let's have a very specific scenario in mind. Okay? One we've certainly talked about before. Let's take a block sitting on a horizontal tabletop. Let's make the tabletop frictionless. Let's not worry about friction for now. And let's reach in and with what we call an applied force, us, let's pull the block to the right. I have drawn a picture showing the block. And what we've done here is the block started at the point labeled 1 on the left, and it's ending up at the point labeled 2 on the right. Okay? So the block has moved from point 1 to point 2 on the horizontal table. That means the block has a displacement vector that starts there and goes from point 1 to point 2. Delta R arrow, displacement. Okay? All right, so our block, our particle, undergoes a displacement, in this case, from point 1 to point 2. And we use delta R arrow to represent that displacement vector. As the block is moving from point 1 to point 2, my free body diagram shows all the forces that are acting on the particle. And you should be able to draw the free body diagrams. Given what I've told you, there are 3 forces acting on the particle. Good old F grav, vertically down. The normal force, perpendicular to the tabletop and upward. And then there's my applied force, which apparently, according to the picture here, is up and to the right. The picture even implies that my applied force makes an angle phi, some angle, relative to the horizontal thing. Notice my axes, x and y. X is horizontal to the right, y is vertically up. Now this, my point is, all of these forces, and including my applied force, are constant as the block moves from point 1 to point 2. I'm being very careful with my applied force to change neither the magnitude of my pull nor the direction. That's what makes it constant. I'm being careful not to change the magnitude or the direction. And of course, F-grav is constant. And since we're going on a horizontal surface with my constant applied force, the normal force is constant. So in fact, all three of these forces are constant as the block moves from point 1 to point 2. Okay, that's the scenario. Three forces acting on a particle. Here comes the definition of work. Now, the way I'm going to denote it, this is the way I recommend you denote it. Here's the notation we're going to use. Start right here inside this blue box with the first symbol. Symbol for work, capital W. That seems reasonable, right? Capital W. But I add a subscript right there. And the subscript is the symbol of the force that is doing the work. So what I'm going to do here in this picture is write for you the formula for calculating the work done by that applied force F. So I've denoted it W sub F. It's really important to put that subscript, I claim, because you got to tell me, which work are you calculating? The work done by which force? Otherwise, people are confused. I'm talking about the work done by the applied force F. It is defined to be 3 lines. And now you know why I introduced the concept of scalar product in the earlier video, because I'm going to need it now for this definition of work. I take the force that's doing the work, that's a vector, F arrow, and I take the scalar or dot product, see the dot there, with the displacement vector, delta R arrow. Okay? All right, now I'm going to get rid of that stuff so it's not so cluttered. F dot delta R. That's the definition of the work done by a constant force F. The force dotted into the displacement. The scalar product of the force and the displacement. F dot delta R. Again and again and again. Say that in your head. F dot delta R. F dot delta R. Really important definition. Now, we wrote down how to calculate scalar product in the previous video for any two vectors. Let me remind you of what that was. Now my vectors are F for the first one and delta R for the second. So, how do you do scalar product of two vectors? You do the following. Take the magnitude of the first vector, so the magnitude of the applied force, times the magnitude of the second vector, magnitude of the displacement, times the cosine of the angle between those two vectors when they're drawn with a common tail. That's what that phi means. Angle between the force and the displacement when drawn with a common tail. That's what the phi should be. Now look at my picture up above. It's a little sneaky. The F, the applied force F, and the displacement delta R, see them both in the picture? They're not drawn with a common tail. So maybe we ought to redraw a little bit. I'll do it down here below. First I'll draw the delta R. It points straight along the plus x direction from point 1 to point 2. Okay? Now let me draw the applied force F, but let me slide it from the original picture so that it has a common tail with the displacement. I can't change its magnitude or direction of F, but I can slide it. And if I do that and draw the F with a common tail with delta R, then that angle phi is the angle between F and delta R. And it's the same phi that's up here. But I got to make sure I can correctly identify what is the appropriate angle between F and delta R. And the pictures aren't always going to draw them with a common tail. But that's the angle I have to use in the cosine, the angle between F and delta R when drawn with a common tail. Let me emphasize even a little more about how that can get a little bit tricky sometimes, all right? All right, so I'm going to erase this stuff right here. You've had a chance to see that. Let me draw for you just a slightly different, kind of a generic picture of two vectors. I'll call them A and B, okay, in an XY coordinate system. Let me draw an XY coordinate system, or part of it. And now let me say, what if I gave you a vector A in a drawing, like that, and I tell you, I'll draw a dotted line in the plus x direction, that this angle right here is 30 degrees. And then I give you another vector B, and I'm going to draw it completely over here somewhere. And it's directed that way. And I'll draw another dotted line in plus x for reference, and I'll put a right angle symbol there. I'm being really sneaky here. And I'll tell you the magnitude of A, and I'll tell you the magnitude of B. There's a number with units for each one. And I ask you to calculate A dot B. How would you do it? A dot B. If I gave you the drawing like that, and it's quite likely I could give you a drawing something like that. Well, take the magnitude of the first times the magnitude of the second times the cosine. We're used to symbol phi, but you have to understand phi just means the angle between them when they're drawn with a common tail. So I need the angle between A and B when they're drawn with a common tail. My point is, it would be incorrect to just put 30 degrees there, because that might be what you might be inclined to do, because you see a 30-degree angle drawn in the picture. So why can't I just do cosine 30, multiply by magnitude A and magnitude B, and be done? Well, do you see that that would not be the correct angle to put in there? Because the phi there has to be the angle between A and B when they're drawn with a common tail. Maybe we should redraw the B, slide it around so that its tail coincides with A. Right? You can do that. You can slide a vector around if you don't change its magnitude or direction. This angle here is a right angle. Now they're drawn with a common tail. Phi, then, you need to see, is that whole angle right there. That's the angle between A and B when they're drawn with a common tail. And you see how big that is? It's 90 plus 30, or 120. Okay, so be careful when you calculate scalar product using the cosine phi formula. The phi has got to be the correct angle. The angle between the two vectors when they're drawn with a common tail. All right, now, that's very important. However, that being said, let me remind you from the previous video lecture that there's another way to write a scalar product. And it's the form to use when you're given the two vectors in unit vector notation. So suppose I'm given the constant force F and the displacement vector delta R in unit vector notation. The way that would be written, I'll do it over here to the side, is F arrow is equal to F sub x times I hat plus F sub y times j hat plus F sub z times k hat, where Fx, Fy, and Fz are just numbers in newtons. That would be the force in unit vector notation. The displacement vector delta R in unit vector notation, using the notation from chapter 4, would be change in x times I hat plus change in y coordinate times j hat plus change in z coordinate times k hat. Or delta x, delta y, and delta z are numbers in meters. That's what, suppose I'm given the F and the delta R in that notation. Then the first line for calculating work, F dot delta R, magnitude of F, magnitude delta R cosine phi, is a bit of a pain. But the second way I taught you to calculate scalar product is perfect, right here. Take the x components of the two vectors, multiply them, plus the product of the y components, plus the product of the z components. So in this case, that would be f sub x times delta x, product of the x components, plus f sub y times delta y, product of the y components, plus f sub z times delta z, product of the z components. So both those two forms in the blue box, both those two equations, are mathematically equivalent. The version you use depends upon the information you're given. Let me emphasize, since by definition, work is the scalar product of force with displacement, we learned in the previous lecture that scalar product is a scalar, hence the name. That means work is a scalar quantity. Good, 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 good. Work is not a vector. Don't ever say things like the x component of the work or the y component. There are no components to work. It's a scalar. What are the SI units of work? Well, from the definition, F dot delta R, it must be the unit of force, Newton, times the unit of delta R, displacement, meter. Newton times meter. And the convention, by the way, is that when you talk about work, that's how you write the unit, Newton times meter, just like you see there. However, it is definitely true, I showed this in the previous lecture, that the unit Newton times meter is equivalent to the unit of energy, the joule, capital J. So you will see people write the unit of work as joule. Just remember that joule is equivalent to Newton times meter. Now, fine, I've given you a mathematical definition of work done by a constant force. And that's how we will calculate work done by a constant force, using the two versions that you see in the blue box. But what physically is work? What does work mean physically in a given situation? I'm going to tell you that now. Physically, work is the transfer of energy between a system and its environment or surroundings by means of a force. Work is transfer of energy. That's what work is. Transfer of energy between a system and its environment, its surroundings, and this transfer is accomplished by means of a force. As we progress in our understanding of physics this year, we're going to introduce other methods for transferring energy between a system and its surroundings. This is just our first method for transferring energy between a system and its surroundings, and it's called work. And it's transferred by means of a force. Remember what I said, forces do work. Little tip, don't underestimate the amount of practice it's going to take to learn how to do the work calculation correctly. That is to say, to apply the boxed equations here correctly. It turns out, a lot of practice. I'm going to start with some right now that I'm going to have ask you to do for class engagement on Blackboard. Let me show you the situation. We're going to practice with work done by a constant force. Here's the scenario. We've got some cases below, and it turns out there are 4 of them. In each of the cases, a particle undergoes a straight line displacement of some amount d, arrow. That's how the book's going to call it in this case. We could also call it delta r arrow, but we might as well get used to the fact that physicists sometimes use different notation for displacement. So I'll use d. And it does this displacement d, well, acted upon by a force, I should probably say, emphasize. It's a constant force. F arrow. Okay, so got a constant force acting on a particle, and the particle is having a displacement d. In each of these cases, your task is to state whether the work done by the force is a positive number, a negative number, or zero. Right? So I'm talking about the work W done by this applied constant force F. Is it a positive number? Is it a negative number? Or is it zero? And I will give you a very big push in the right direction. The focus of your thinking should be how we defined work done by a constant force, force dot displacement. So that's what I'm going to use. Now, because of the notation in this problem, I'll write D arrow for displacement, but that's just a change in notation, not a change in definition. The work done by a constant force is force dot displacement. Scalar product of force with displacement. You need to use what you have learned about scalar product to tell me in each of these four cases whether the work done by the force is positive, negative, or zero. Notice in the first case, all I'm telling you is that the angle between the force and the displacement is 30 degrees. In the second case, I'm telling you that the angle between the force and the displacement is 120 degrees. Third case, the angle between the force and the displacement is 90 degrees. Fourth case, just to switch it up a bit, I'm going to tell you the force and the displacement each in unit vector notation. But in all four cases, all you have to do is tell me 1, 2, 3, 4. W is greater than 0, W is less than 0, or W equals 0. So please answer this for class engagement. On Blackboard. Okay? That's a little bit of practice, just the beginning practice with calculating work. We'll be doing a lot more. Now there's one more important idea in the reading in Chapter 7, Section 2. I want to talk about that now. And that idea is a pretty big one. It's called the work kinetic energy theorem. Wow, theorem. That sounds rather like a mathematician talking, because theorem is something that mathematicians use. A theorem is something you can prove. So the work kinetic energy theorem apparently can be proved by using mathematics. And that's because, I'll go ahead and tell you right now, it's just Newton's second law, dressed up to look like it's in a disguise. You can start with Newton's second law and prove this theorem called the work kinetic energy theorem. So it's really just Newton's second law dressed up in a new suit, so that you might not recognize it at first. But I think it's helpful to remember that. It's an alternative way to write Newton's second law. But it uses the concepts of work and kinetic energy, which we have both defined. So here's a statement of the theorem without any proof. You want to see the proof, by the way, or at least a somewhat simplified version of the proof? Read Chapter 7, Section 2 in our book. I'm just going to state the theorem. All right, here's the backstory. When work is done by the external forces acting on a particle, energy is transferred to or from the particle by the surroundings, by means of the force. Here's the result of that energy transfer. The net work done by all the forces acting on the particle equals the change in the particle's kinetic energy. That's the work kinetic energy theorem in words. There's some really important words here. Net is a very important word. It's got to be the net. Net means total, right? The total work done by all forces acting on a particle equals, here's another important word, the change in the particle's kinetic energy. The hint that this comes from Newton's second law is that it's net work, and Newton's second law included net force. And change in kinetic energy and Newton's second law included acceleration, which is all about change in velocity. So there are little tantalizing clues in the wording here that this is coming from Newton. Okay? Say it one more time. The work kinetic energy theorem states, the work done by the net work done by all the forces acting on a particle equals the change in the particle's kinetic energy. Now we write that same thing in symbols. W net, total work, net work, is equal to change in kinetic energy. That's really it right there. Right there. W net equals delta K. Okay? Now, there are other ways to write the delta K, okay? And we should talk about those. Change in kinetic energy means final minus initial. Your book writes that as K2 minus K1. K2 is the final kinetic energy, K1 is the initial kinetic energy. So K2 minus K1 is delta K. Of course, kinetic energy means 1/2 m times speed squared. Now we're using the shorthand notation for speed squared, like I talked about in the previous video. So you could write K2 like that, 1/2 mv2 squared, 1/2 m final speed squared. And you could write K1 as 1/2 mv1 squared, 1/2 m v initial squared. So you'll see that delta K written these various ways, depending upon how useful that is. Okay? But the idea is W net equals delta K. I can't emphasize too strongly that it's change in kinetic energy that happens when net work is done. Now there are three kind of scenarios that go with this result that I want to talk about one by one and give you a physical example of each. These are not necessarily in order of importance, but here's the first one. Suppose we have a situation where the net work done on the particle is greater than 0. It's a positive number, it's greater than 0. Then this theorem tells me that the change in the kinetic energy must be greater than 0. The final kinetic energy is larger than the initial kinetic energy. This has to mean physically that the particle speeds up. Because in order to have K2 greater than K1, from the formula for kinetic energy, V2 must be greater than V1. The V's here mean speeds, not velocities. So the final speed is greater than the initial speed. The particle speeds up. Let me give you a case where that could happen. Let me draw a little picture down here. There's the ground. And we're going to take a particle. Let's suppose it's a tomato. So I'm drawing it here in red. And all I'm going to do, I'm holding it in my hand, is let go, release it. Okay? That means at the moment I let go, its initial speed, v1, is 0. Of course, we know that it will fall vertically down until it goes splat against the ground. But just as it reaches the ground, it will be traveling downward with some speed, v2. That is definitely not 0. Okay? All right, so all I did was release a tomato and let it fall vertically under the influence of gravity. Let's think about the work kinetic energy theorem between point 1 and point 2. Okay? All right, let's draw the displacement vector for the tomato between point 1 and point 2. I'll draw it just over here to the side. It would point straight down, yes? From point 1 to point 2. There's delta R arrow. Let's draw the force vector. Which one? The only force that's acting once I let go. F grav. Let's draw it with a common tail to delta R. I'll draw it just beside it right there. Of course, F grav points down, right? But I've drawn it with a common tail. It acts, of course, all the way down. But all you have to do is draw it in order to think about work with a common tail with the displacement. So that's an important drawing sketch for this situation. Now all I'm asking you is, What's the sign of the work done by the gravitational force? Notice how I wrote that. WG. Work done by the gravitational force. Is it positive? Is it negative? Or is it zero? Pause the video, think about that, and then come back. All right. Well, the work done by the gravitational force, since that force is constant, is F grav dot delta R. That's magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between those two vectors when they're drawn with a common tail. Do you see that the angle phi in this case is 0 degrees? Yes? Because both those vectors, F grav and delta R, point in the same direction, vertically down, so the angle between them is 0. Cosine of 0, please remember, is positive 1. And of course, magnitude of F grav and magnitude delta R, magnitudes can never be negative. So my whole point of this is that the work done by gravity in this case is a positive number. It's bigger than 0. That means the change in the kinetic energy, work kinetic energy theorem, must be greater than 0. That means the final kinetic energy, K2, must be greater than the initial kinetic energy, K1. Well, in fact, the initial kinetic energy was 0. It started from rest. And the final kinetic energy is bigger than 0 because V2 is not 0. It speeds up. There, the particle sped up. So we had W net, because W grav is W net, was greater than 0, and so the particle speeds up. That's one possibility. Now I want to do another case. If you have the case where the net work done on the particle is a negative number, it's less than 0, then the work kinetic energy theorem says the change in the kinetic energy is a negative quantity. That means K2 is less than K1. The final kinetic energy is less than the initial kinetic energy. That means the particle slows down because the final speed, V2, must be less than the initial speed, V1. So if W net is a negative number, then the particle slows down. Let me draw that. Okay, let me just adjust my drawing a little bit here. Okay, all right, let me see. How do I adjust my drawing over here? All right, get rid of that, get rid of that, let me get rid of that. Okay, now here's what I'm imagining. In this case, let's take the tomato and have it start at ground level and just throw it so that it has an initial velocity up. But all my throwing is doing is giving it the upward initial velocity. So I'll draw a red arrow upward and label it V1 to use our notation now. But now I've let go. I'm not touching it anymore, so the only force acting on it is gravity. This is a chapter 2 problem, right? It'll go upwards, slowing as it does, and it'll have some maximum height up here, and that's going to be my point 2. And for just one moment in time, its speed at that point 2 is 0. I'm just focusing on that part of the motion. You understand? The part where I had just released it, it's traveling up, slowing, and it's currently, point 2 is at its highest point, momentarily at rest. Let's apply the work kinetic energy theorem to point 1 and point 2 in this picture. Okay? All right, now there's an important change to the other part of this diagram, the delta R. Do you see the important change to the delta R in this case? The displacement points from the first location to the second location. So now it starts on the ground and it goes up. So the delta R, the blue arrow representing delta R, now points up. Pause and let that sink in a minute. The displacement vector is up. Now let me draw the F grav. That's the only force acting, but let me draw it with a common tail with delta R. So I'm going to draw the F grav with its tail there, but of course F grav points down. And label it. You see what I'm saying? You always want to draw that force and the displacement with a common tail. If you've got to slide the vectors around to do it, okay. slide them around. Now you should be able to identify the angle phi between them, between the F and the delta R. That's it right there. That's what goes in here over here in the work calculation where the phi is. And what is that angle? It's a whopping 180 degrees. Picture is important. The delta R is up, the F grav is down. Draw them with a common tail so that you can identify the angle phi between them. Then remember that the cosine of 180 degrees equals -1. Now multiply that by the magnitude of F grav, which is positive, and the magnitude of delta R, which is positive, and you end up overall with a result for the work done by gravity that's a negative number, less than 0. Okay, so in this scenario where the tomato is traveling upward under the influence of gravity, the work done by the gravitational force is a negative number. The work kinetic energy theorem then tells me that the change in the kinetic energy is a negative number. Change in the kinetic energy is negative. That in turn means that the final kinetic energy is less than the initial kinetic energy. It's slowing. It slows down. Of course, that's exactly what a tomato would do, traveling upward under the influence of gravity. It would slow down. So that's another possibility. If the net work done on the particle is negative, the particle has to have slowed down. Now there's one other case I want to consider. If the net work done is 0 on a particle, then the work kinetic energy theorem tells me that the change in the kinetic energy is 0. That means that the particle has the same final and initial speeds. V2 equals V1. Please note, don't overread that, don't overinterpret it. I'm not saying that the particle never moves. It might not be moving, but it might be moving in between point 1 and point 2. But the speed at point 1 and the speed at point 2, the speed at the beginning and the speed at the end are the same. I can give you a situation where that's happening. Go back to the tomato. And now consider this. Point 1, just as I release it when I've thrown it upward, just like you see here in my drawing. But now I'm going to, on purpose, pick a different point 2. Not at the high point, but let it fall back down. And now let point 2 be just before it hits the ground on the way down. So it's traveling downward, like that, with some speed v2. But you think about what we learned in chapter 2, this speed, magnitude of the velocity initially, and this speed, magnitude of the velocity just before it hits the ground on the way down, they're equal. Because it speeds up on the way down just as much as it slowed on the way up. So for this tomato, the initial speed v1 and the final speed v2 are equal, even though the speed was changing in between. Therefore, the change in the kinetic energy between point 1 and point 2 is 0, and the net work is 0. How is the net work 0? Well, I have negative work done by gravity on the upward leg, and the same amount of positive work done by gravity on the downward leg. And so the total work done is 0 by gravity. So that can happen too. It has to be clear from the situation what point 1 and point 2 are supposed to be. And then you've got these three cases. Is W net greater than 0? Is W net less than 0? Or is W net equal to 0? Okay, that's going to be where we stop for this second part of video lecture 7.1. And in class, we will be practicing with the ideas of work and kinetic energy. That's all for this video.